Okay, so we're recording now. So once again, the homework assignment for next Sunday is on the class website, and I think I sent you all a PDF on it. I also added a PDF both to the website and to the email on a little more about how to use MATLAB to solve differential equations. So let's see where we were. The associated Legendre polynomials is, I think, what we were talking about last time, although we had gone a little bit beyond that. We see them in electrodynamics often in this form, in the on a more compact notation with x equal to cosine theta. So where is my, oh my God, where is my Apple Pencil? Oh God. Hold on just a sec. Yeah, I looked in the easy places. Okay, so I don't know where the Apple Pencil is. So I don't know quite how I'm going to deal with this. So I'll just try to carry on without it, at least initially. It's okay, so the more compact form for the Legendre polynomial, the associated Legendre polynomial PLM of x is this equation 998. And this PLM is actually the m over 2 power of 1 minus x squared times the nth derivative of the nth Legendre polynomial. And the proof of that is given in these pages. I don't think we need to go through it step by step. Let me just shut this door. The Legendre polynomial has a symmetry PLM of minus x as minus 1 to the L plus m PLM of x. And consonants shortly have a different definition, but I think this is, anyway, if you're ever doing a serious calculation with them, make sure that you adopt one consistent notation. And if you're working in a group, make sure everybody's using the same notation. You don't want some people using consonants shortly and other people using what I think is the more standard notation. Rodriguez's formula for the associated Legendre function, I can pop back to that if you want. That is, the Rodriguez's formula just looks like this. And it's clear here that if m is greater than L, then we have 2L derivatives of something whose highest power is x to the 2L, and you get 0. Similarly, if m is less than minus n, then there are no derivatives at all, and we also have 0. Anyway, so the index m goes in integer steps from minus L to plus L. And we normally interpret m as the z component of the angular momentum. When m is not 0, there's a power of this square root in it. And of course, if x is cosine theta, this square root is just sine theta. So the associated Legendre functions are really polynomials in cosine and sine of theta. Now, if we write the equation satisfied by the associated Legendre functions, I think we saw that equation earlier. It looked a little different this second time. No, there's still an m squared here. So if we look at that equation, we can think of this in two different ways. We can think of L plus 1 as the eigenvalue, or m squared as the eigenvalue. If LL plus 1 is the eigenvalue, then the weight function is unity, because that's the thing that multiplies the eigenvalue. And since the ODE is self-adjoint on this interval, at the end of which p, little p, vanishes, the eigenfunctions must be orthogonal on that interval when L is not equal to L prime. And then one can derive this integral formula that PLM, PL prime M is this combination of combinatorics times, the important thing is delta L, L prime. On the other hand, one can go back to this equation and say, no, this is not the eigenvalue. This is the Elf equation. This is the eigenvalue. And if you do that, you say m squared for fixed L is the eigenvalue, and then the weight function is 1 over 1 minus x squared. It occurs in the orthonormality relation. And now we have a delta of m and m prime. So those are two different ways you can look at this system. The spherical harmonics, well, these are defined, these are called YLM, and they're the associated Legendre function times an e to the im phi multiplied by a square root of combinatorics. So there's e to the im phi over root 2 pi, and then the big cat, this is capital Greek theta. This is this combinatoric factor times p. And obviously the phi component satisfies this equation. The spherical harmonic satisfies this equation that occurs over and over again in quantum mechanics classes and also in electrodynamics classes. The big square root here gives us orthonormality in L and M for the spherical harmonics. So the spherical harmonics are these y's. And if you have a parity transformation, you flip x, y, z to minus x minus y minus z, then that's like r prime is r, theta prime is pi minus theta, phi prime is phi plus or minus pi, and cosine theta prime is minus cosine theta, e to the im phi prime is minus 1 to the m e to the im phi, because e to the im pi is minus 1 to the m. Anyway, what happens is that the spherical harmonic under this parity transformation is transformed by a factor of minus 1 to the L. And so we say in quantum mechanics, the state NLM has parity minus 1 to the L, and this leads to various selection rules in atomic and nuclear physics. The spherical harmonics are complete on the sphere, unit sphere, and they can be used to expand any smooth function in this way. Now, why are they complete? Well, the e to the im phi is just a Fourier series on the intervals 0 to 2 pi. And it's got to be periodic if we're talking, we're saying that all angles 0 to 2 pi are physical, then the thing is nature's periodic rotating. The other ones are the other part of the orthogonal of the completeness is the associated Legendre functions, and these then are complete on the interval -1 to 1. The orthonormality of the YLMs guarantees that that if we make an expansion of an arbitrary function like this, the ALMs are going to be given by Y star F integrated, because the Y star just picks out, it gives you delta L M, delta LL prime, delta MM prime, and picks out the ALM coefficient. If you put those two things together, what you see is you've got F as written in terms of F and this big integral. So all of this thing, the stuff between the square brackets is an angular delta function. And you can think of it as delta theta minus theta prime, delta phi minus phi prime divided by sine theta. And that just knocks out this back to here. And so this is the completeness relation for the associated Legendre polynomials, sometimes written this way. We had a spherical harmonic expansion of the Legendre polynomial earlier. Well, no, not earlier. If we do a spherical harmonic expansion of the Legendre polynomial with PL of n dot n prime, then what you can do is expand it in terms of, if you think of it as a function of theta and phi, you can expand it in terms of the YLMs of theta and phi. If you think of it as a function of theta prime and phi prime, you can expand it as a function of as a sum of YLMs of theta prime and phi prime. The complex conjugate doesn't really make any difference because PL is real. The remarkable thing is that if you do both, if you do one, you get the other, and you get this remarkably simple formula. This is called the addition theorem. Let's see, yeah, it's called the addition theorem for spherical harmonics. The derivation of it is in the chapter on group theory. There's a group theory derivation there. One application of these spherical harmonics, of course, is to describe the CMB, the cosmic microwave background radiation. We have this lovely photograph, well, plot, I guess, of the microwave background radiation. The blue regions are cooler, the red ones warmer, but only by about 300 microkelvin. The average temperature is 2.7255 Kelvin, and this thing is it's the best black body we have. In other words, if people go into the laboratory with a grant for $1 million and set up a black body generator or try to make a black body, they're not going to do as well as the universe's black body. The gray outline here is the outline of our galaxy. And so that just puts it in perspective. So here, if you're looking, I guess, well, I don't know, I'm not an astronomer, but if you're looking, all right, let me guess that this is the way it goes. You're looking east, these are the points. You're looking west, these are the points. And if you look, east enough and west enough, eventually you're looking in the same direction. Similarly, if you look, this is the North Pole, this is the South Pole. Well, it's not quite similar, is it? It's a little bit different because the North Pole, you look out in the North Pole, you're not getting the same thing as you're looking out at the South Pole. Anyway, this is the microwave background radiation, and it's something such that I think people could, by the way, these are other nearby, these are the galaxies, the tiny galaxies that orbit around our galaxy, dwarf galaxies, I think they're called. This, I mean, I could stare at this for quite a long time, and I think I'll leave it to you to stare at it. What the physicists and astronomers who were studying the CMB did was they, of course, expanded the temperature distribution in terms of spherical harmonics, and the coefficients then are given by integrating the temperature times YLM star over the whole sphere. A little background here, the instruments on the Wilkinson microwave anisotropy probe, that's WMAP, and Planck satellites at the Lagrange point, which is in the Earth's shadow, about 1.5 million kilometers farther from the sun. They've measured the temperature, and that's the plot we saw in the figure that I just displayed. This is radiation from photons when the photons emitted when the universe became transparent. And the universe became transparent when the hydrogen atoms, when the temperature of the universe dropped enough so that the hydrogen atoms were basically in their ground state, and the temperature was well below 13.6 electron volts, whatever that is in Kelvin. That's around 1,000 degrees Kelvin, I think. And actually 3,000 now that I see it here. And at 3,000, the universe was, the photons were cold enough, so the Planck distribution of photons at that point was cold enough so that they very rarely were able to excite an atom from a hydrogen atom from the ground state to the first excited state. And of course, this distribution of photon energies went, you know, looks like that. Well, it looks like that. And you had to suppress the tail. So it wasn't enough to just not be able to excite the first state. You have to be well below the temperature required to exactly get to the first state. You need to be such that even the photons in the tail of the Planck distribution are too weak to excite that first state. Anyhow, sorry for all this. This happened at about 380,000 years after the Big Bang. I call this initial transparency. Some people call it decoupling. It's when the photons and matter essentially decoupled. The photons and the hydrogen decoupled. The helium decoupled more earlier because helium energy levels are higher. And the universe, apart from dark matter, which we don't understand at all, the matter that interacts with light is hydrogen. After the Big Bang was basically hydrogen and helium, and then in the first 3 minutes, right after the Big Bang, it was basically quarks, gluons, and all the elementary particles. But then they settled down to be neutrons and protons and photons and then dark matter. And by the time 3 minutes went by, the neutrons and protons, the neutrons had all either decayed or become absorbed in helium nuclei, or deuterium, which is 1 neutron, 1 proton. But most of the stuff that was left behind was hydrogen, and that's the hydrogen gas. Okay, well, Anyway, so, and it was around 380,000 years after the Big Bang that decoupling occurred. Astronomers also often call this by another name, which I have mercifully forgotten, and because it's an inappropriate name. It's called recombination, and it only makes sense if there previously been a combination of hydrogen and of protons with electrons, and we have no knowledge of that, and the theory doesn't posit that, so it's kind of silly. Here's the agreement that people analyzing the Planck data in terms of what's called the Lambda Cdm model. Lambda is the energy of empty space, or the cosmological constant equivalently, and CDM is cold dark matter. And so that picture of the universe, it doesn't mean that there's nothing but lambda and cold dark matter. It's that there's lambda, cold dark matter, and then ordinary matter. Anyway, this is the fit they have where, let me go on a little bit before coming back to this. The average temperature only contributes to A00. Remember, these A's are the coefficients of the temperature distribution. If you sum over M, the squares of the L's, divide by 2L plus 1, you get something the astronomers called, or the CMB people called C sub L. And the only C sub L that the average temperature contributes to is C0. Now, if the unit vector n points in the theta phi direction in the sky, and you use the addition theorem, then we can write the power spectrum of some of these squares as well. What we do is we take this times its complex conjugate, so then we have a y and a y star, and a t of n and a t of n prime, and that sum of a y and y star gives us a PL of nn prime. The measured values of the power spectrum multiplied by L plus 1 divided by 2 pi are plotted here, and against L between 1 and 2500. The high L's, of course, are the ones that are sensitive to very small angles, whereas the low L's are things like, cosine theta, and that takes in the whole sky. So these are huge angles, small angles. And if you're looking at the small angle stuff, well, that stuff is all over the sky, and so we have very, very accurate data. But as we go to the large angle sky, well, we only have one sky, and so we have very little data, and so that's why these points are terrible, are not very accurate. The angle versus multipole is roughly 180 over L, and this is a snapshot then. This power spectrum, maybe I should write this. Maybe I should do this way to keep the power spectrum clear. Oh my goodness, where did we go here? What is this? This is crazy. Why am I? Oh, hold on. I'm going to try to get us to. Okay, that's good enough. All right, so this figure here is the measured values, and they're plotted, and you can see that, the blue curve, of course, is the curve that is the theoretical curve based on lambda cold dark matter, and you can see, and 6 parameters. So there are 6 parameters here, and just to reduce your amazement or explain things a little bit, one of the parameters fits the height exactly here. Okay, so It's not as though pure theory got this height. Instead, one of the parameters gives you the height. And what are these bumps? Well, first of all, this power spectrum basically is a snapshot at the moment of initial transparency of the temperature distribution of the rapidly expanding plasma of dark matter, photons, electrons, and nuclei undergoing tiny acoustic oscillations. And tiny means that the oscillations were like 2 parts in 10 to the 4th. And in these oscillations, you had gravity fighting radiation pressure. So the radiation pressure was pushing things out, gravity was pulling things down. And so basically, when everything gets compressed the most, you have the highest temperature. When the thing is expanded the most, you have the lowest temperature. And so the regions that gravity has and pressure have, or the gravity is squeezed to maximum compression, form the first peak. So that's the first peak of showing the regions that are collapsed. On the other hand, are collapsed at the moment of transparency. On the other hand, regions that have bounced off their first maximum compression and that radiation is expanded to minimum density form the second peak. And then the third peak is maximum compression, maximum rarefaction, maximum compression, and so forth. So that's basically the way that's to be understood. As I said, the blue curve is a model of the prediction of inflation, cold dark matter, cosmological constant lambda. And in the Lambda Cdm model, the age of the universe is 13.8 billion years. The Hubble constant is 67.7 kilometers per second per megaparsec. And a megaparsec is 3 million light years roughly. The energy density of the universe is enough to make the universe flat. And the fractions of the energy density due to ordinary matter, dark matter, and dark energy are roughly 5%, 26%, and 69%. So some things that we learned from the data and from the agreement and what was used to derive that agreement is first of all that the speed of sound in the plasma, the speed at which longitudinal vibrations progress in the plasma is roughly the speed of light over the square root of 3. And now the expansion of the universe has stretched the wavelength of light and reduced its temperature from 3,000 down to roughly 3 Kelvin, an expansion factor Z of about 1100. And the radius of the maximum compression region is now longer. The radius is longer by a factor of about 1100. And our distance to the surface of last scattering is also stretched by a similar factor. Anyway, a careful analysis based on general relativity and a model of a flat universe with cold dark matter and dark energy gives the solid curve that I mentioned. And it's great agreement for L greater than about 30. The maximum of the power spectrum is at about L equal to 200, an angle of 0.6 degrees. And this agreement tells us the space is flat. If the universe were closed, k equal to 1, the angle would appear bigger. If it were open, it would appear smaller. And the heights and locations of the peak tell us about the density of baryons, the density of dark matter, and much more. There are many, many papers put out by the Planck collaboration. I personally think they could have done a better job explaining things, but maybe I'm just being overly critical. Anyway, let's see, do I have any questions in the chat box, or has anybody asked a question? Let me see if I can at least make sure that the chat box is actually open. So let me, all right, there's the chat box, but I don't see anything in it. So maybe somebody can say something. Either shout or write. So let's see, we want to make this one. So we're basically finishing the, oh, by the way, I wrote a paper on this stuff. You can find the reference here. What is it? Your JPhys. Well, I'll put it on the class webpage. It's a sort of a pedagogical discussion of decoupling and an analysis of the CMB and some other things about general relativity that you may not have been taught yet. Anyway, what are the Bessel functions? Well, there are several different kinds of Bessel functions, and the first kind and the simplest ones are defined for positive or non-negative integers, and they're basically given by an infinite series like this. And first term tells us what the Bessel function is like at small z, and it goes as z to the n over n factorial. So what you learn immediately here is that if n is a positive integer, all the jn's are 0 when z is equal to 0. On the other hand, j0 is 1 as z goes to 0. So there's the boundary conditions are sort of a step function in boundary conditions. For n equals 0, it's 1. For integral n positive, it's jn of z is jn of 0 is 0. Because these signs alternate, and that's the -1 to the m, you get waves. And these are here's J0, and you see it starts out at 1. And then J1, let me see, the J1 is this one, the dot dash, and then J2 is the dashed. And then the others, or some of the others, J3 is solid, J4 is dot dash, J5 is the dashed one. And so they are progressively calmer. Oh, it's going to sleep. Progressively calmer Bessel functions, longer wavelengths. There's an approximation for large z, as we send z to infinity, 1 over root z, a cosine, and then an order of magnitude estimate of the next term. The Bessel's equation, the JNs, by the way, you can see that their power series in Z, and moreover, they're going down as n squared, n cubed, and so forth. And you've got an n factorial here, you've got m factorial times m plus n factorial. I mean, they're incredibly convergent. So they're entire functions. The Bessel functions are entire functions. They obey Bessel's equation. And once again, there is this magic generating function, which always amazes me. So this magic generating function is e to the z over 2 times u minus 1 over u, and that gives you a sum u to the n jn of z, n going from minus infinity to plus infinity. And one can then derive the series expansion. And one can also derive this integral representation. And in particular, you learn something from this integral representation, that if you take n and replace it by minus n, you get a factor of -1 to the n. If you reverse n and z, nothing happens. Jn of z is equal to j minus n of minus z. So there are these crazy symmetries, and these are true for complex z. For n equals 0, this integral is somewhat simpler, and they show in particular the Jn of 0, 0. So if you put z equal to 0 here, you just have 1. I'm sorry, I screwed this up completely. If you set n equals 0,
Yeah.
what you get, I mean, sorry, you set z equal to 0, you have just the integral of 1 integrated from 0 to 2 pi, divide by 2 pi, you get 1. So j of 0, 0 is 1. On the other hand, j n, what am I saying here? Jn, which is up here, of 0, in fact, is 0. Well, it's a little bit less obvious. Oh no, it's not. It is kind of obvious. It's cosine of n theta integrated from 0 to pi, and the cosine starts out, goes down, and so it's equal to 0, the integral. Anyway, if you differentiate the generating function with respect to u, remember the generating function is this magic equation here, and you identify coefficients, powers of u, you get these recursion relations. And now the original definition, of course, of Bessel's function was this power series expansion involving m factorial and n factorial. But we know that n factorial is related to the gamma function, and the gamma function is basically a meromorphic function. It's defined, it's analytic everywhere except at negative integers, basically, maybe 0. I forget whether or not it's 0. But anyway, you then can extend that definition by using the gamma function. And so now we have non-integral values of nu. In fact, it could be complex nu. So maybe I should say, so this is the series for general nu. Now the self-adjoint form of Bessel's function, if we said z equal to kx, is this. And now you see the k squared has popped out. And in this notation, p of x is x, k squared is an eigenvalue, and x is a weight function. And to have a self-adjoint system on this interval, we need this boundary condition for all functions in the domain. At we have J0 is 1 at the origin and Jn is 0 at the origin. Since p of x is x, the terms in the boundary condition vanish at x equals 0 as long as the domain consists of functions that are twice differentiable on the function, on the interval, I'm sorry. And on the closed interval, let's say, so that they're bounded there. And to make the terms vanish at x equal to b, we require that Jn of kb vanish and that v of kb. So these are extra conditions on the domain and the adjoint domain. And so then KB has to be a zero of Jn of Z. And so what we say is Jn of KB or Jn of Znm equals zero. Znm is the mth zero of the nth Bessel function. So we set K equal to Znm over B, so that this just gives us that. Then Bessel's equation takes this form. And now P is still X. We've got an eigenvalue that looks like this. And that's the eigenvalue that we call K squared. And it's different for each positive integer M. And as M goes to infinity, the zeros rise as M pi. And that gives us completeness. So I think, so then the orthonormality relation for the J's is that for different eigenvalues, remember the eigenvalues are Z over B. Let's see, Z over B or Z over B squared. Z squared over B squared is the eigenvalue. And X there is the weight function. So we have there delta M, M prime, and then times effectively a normalization factor. And so because they're complete, then sums of Bessel functions can represent Dirac delta functions. And of course, what you need in any of these Dirac delta function sums, you need the function at X, the function at Y, the same function at Y, and then you need to multiply it by some normalization factor, and you need to include the weight function, but the weight function can be distributed alpha parts X and 1 minus alpha parts Y. Or this could have been replaced by just X or by Y. If we set N equal to 1 and B equal to 1, then this sum is somewhat simpler. In other words, we say the interval goes from 0 to 1. And so then to verify this remarkable delta function equation, which represents the completeness of the Bessel functions, I had MATLAB do a plot. And this is then the sum of the first 100,000 terms where I set, so I went over here and I said alpha equal to a half. So this is square root of X, square root of Y. And then did the sum. And let me just say, what is the sum? The sum is on K. So these are all the zeros of the first zero, the second zero, and so forth of the first Bessel function. And the normalization factor is the second Bessel function squared at the zero of the first Bessel function. So this is 0 of J1. It's not a 0 of J2. By the way, a friend of mine who's a physicist, he's actually an Englishman, who, at least when I last spoke with him, was he and his wife had moved to China and were at a leading Chinese university in Shanghai. That's how I know him, because I spent a year there. Anyway, he told me once that his father was in the British Navy, and his father told him that during the Second World War, the zeros of the Bessel functions were military secrets in the United Kingdom, which is kind of funny. You see, we treat them quite casually now, and we can compute them with MATLAB or Mathematica. And whereas back in 1943 or so, they were military secrets, and I guess you could be thrown in jail if you screwed around with them. If you wrote them on a sidewalk. Anyhow, so This delta function expansion means we can expand any function in terms of the Bessel functions, and the expansion looks like this. This whole business is related to this orthonormality relation on this particular integral. Remember, B was arbitrary. Once you pick B, then the eigenvalues are given by the zeros of the Bessel function divided by B. So then the question is, what if you want to go to, say, an infinite interval? And in that case, you still have the weight function out here. I just took it to the power 1. But what you've got as your delta function then is an integral Jn of kx, Jn of ky, and now you integrate over the eigenvalues. So that's quite a nice expression. Here's an example, an exercise. I could either go through this slowly or not, depending on you guys want to vote on this. Do I go through it, or do I skip it and leave it for Wednesday? So let's have some guidance from the class.
I'd like to see it.
Okay, 1 for seeing it. Anybody want to skip it?
Nah, 2 for seeing it.
All right, okay, so Bessel's drum. Well, the top of a drum, of course, is a circular membrane with a fixed circumference, and the potential energy of the membrane is approximately proportional to the area of the membrane. So you can say it's 0 when it's perfectly flat, but when the drum is struck, the surface gets a little bit bigger, and that means that there's some potential energy there, which then, of course, turns into kinetic energy. The extra length of the segment, of the line segment, is 1 plus, if h of x, let's suppose, I suppose I should have used spherical, cylindrical coordinates here, but instead I'm thinking of a square patch of the drum. And if the height has an x derivative h sub x and a y derivative h sub y, then the extra length is basically, the length is dx squared plus dx squared times, well, h sub x squared dx squared is dy squared. So this is dx squared plus dy, well, not dy, dh squared. And this is dy, the square root of dy squared plus dh squared. And then you subtract 1. And so this is the extra energy. There's also some kinetic energy, which is the time derivative of the height. And so this is the potential energy, this is the time derivative. So this is our action formula. Action, remember, is integral of, it's basically integral of the Lagrangian times time. And the Lagrangian is basically the kinetic energy minus the potential energy, at least for simple systems. And we minimize this by saying that the, our equation of motion will be the function of h that that minimizes the action, or that makes the action stationary for small changes in the height. Height is a function of, let us say, x and y. So let me just write a note to myself. I should have done this in cylindrical coordinates from the start, but on the other hand, Cartesian coordinates are somewhat simpler to think about. Anyhow, the change then in the action is the time derivative times the change in the time derivative minus sigma x derivative times change in the x derivative of h, and so forth. And as usual, the change in the time derivative is the time derivative of the change, and the same thing with x and y. And so we integrate by parts, and of course, on the periphery, the circumference of the circle, the edge of the drum, the membrane is tied down. That's how a drum works. And so they all vanish. And what we have left is that this thing in the square brackets has to vanish, and that's the wave equation for the drum. And it says that some mass density times the second time derivative, or the acceleration of the height of the drum, is equal to some constant, I guess, a tension factor times the Laplacian of the height function. And this is a separable equation, so we let h of x, y, and t be s of t, v of x and y. V, I guess, vertical is what I had in mind. And so when we substitute for h, sv, this thing turns into s double dot over s is equal to sigma over mu, Laplacian of v divided by v. This is a function of t, this is a function of x, y. They both then have to be constants. You can call a constant minus omega squared. The eigenvalues of the Helmholtz equation give us the angular frequencies in terms of lambda, as omega is then sigma lambda over mu. And so the time dependence altogether is two constants, A and, okay, somebody's making a lot of noise. Please mute yourself if you're making a lot of noise. It sounds as though you're chewing on the keyboard. Anyway, S of t then is A sine of the square root times t minus t0. In polar coordinates, the Helmholtz equation that we're left, namely this thing, separates, well, that's the polar, that's this. The one we have here is minus Laplacian of v is minus v, the second derivative with respect to r, minus 1 over r, the first derivative, minus 1 over r squared, double theta derivative is lambda times v. And now if we set v equal to some u of r, h of theta, we then get this expression. We multiply both sides by r squared over uh, and we get this. And now the left-hand side is a function of r, the right-hand side, this piece here in the middle is a function of theta. They can only be equal if they're both constants, equal to n squared. So then we set h of theta to some constant b sine n theta minus some theta n. And the n is this square root of this constant. And what's left is Bessel's equation. So the displacement u of r has to obey this equation. This equals n squared. And when you rewrite that, you get this equation, which is a version of Bessel's equation. These things vanish at r equal to the radius of the rim of the drum. And this is then an eigenfunction, Jn of Znm r over Rd. So when r is equal to Rd, this cancels, and Jn of Znm is 0. So if u is equal to this, it satisfies the boundary condition. If it's Jn, it also satisfies the differential equation. And lambda, though, can't be any old real number. It has to be it has to be z squared over the radius squared of the drum. And if we put it all together, then we get that the actual surface of the drum is a function of radius, angle, time, infinite set of constants, and t0 and theta sub n, and actually that should be a theta's t0. It might be a t0 sub n. I'm not sure. Anyway, that's right. I say they can depend on N and M. Anyway, the zero Z and M for big N and big M is approximately that. So this is how the drum beats. And so that's the end of that example. I think I drew it out a little too long. Anyway, Helmholtz's equation, which is minus Laplacian of V is alpha squared V, it separates in cylindrical coordinates in 3 dimensions. And so we write it as B of rho, phi of Z, Z of Z. And the Laplacian is then this in cylindrical coordinates equal alpha squared V. Then if B obeys Bessel's equation and phi and Z satisfy this, or B obeys a slightly different Bessel's equation with a minus sign here, and phi and Z satisfy this, then all of this works. In the first case, the solution is Jn of root alpha squared plus k squared rho, e to the I n phi, e to the plus or minus kz. In the second case, it's Jn of the square root of alpha squared minus k squared rho, e to the plus or minus I n phi, e to the plus or minus I kz. And in both cases, n must be an integer if the solution is to be single valued on the full range of angles from 0 to 2 pi. When alpha is equal to 0, the Helmholtz's equation becomes Laplace's equation, and the functions are a little bit simpler because instead of here, what happens is alpha, let me just, alpha squared is 0, and so we have a k squared here, and we immediately get those. These are more complicated solutions, which we'll get to later. Well, actually, we're getting to them right now. In other words, we have ik rho, and here we have k rho. This ik rho, if you multiply it by I to the minus nu, you get something that's real, and that's called a modified Bessel function. And it occurs in solutions of the diffusion equation, where d is the diffusion constant times Laplacian of v is equal to v dot. And the diffusion equation, of course, is how atoms diffuse in a gas or in a liquid. The function v, again, the Helmholtz's equation separates, and what we have then is Laplacian is equal to this, and if B obeys Bessel functions and phi of Z satisfy this, or this is and that, then the solution in the first case is this, and in the second case is that. And the difference here is that here we have Laplacian V plus Laplacian V is alpha squared V, whereas previously we had minus Laplacian V is alpha squared V. Now, Laplacian is intrinsically a negative operator. I mean, it can have positive values, but it's intrinsically negative. And so minus Laplacian is the thing that's positive. Remember, in quantum mechanics, minus Laplacian is proportional to p squared, of course, being positive. On the other hand, in the diffusion equation, we have a different equation, and it is, in this case, it's plus Laplacian is equal to the time derivative. And the solutions that one has, if it's Laplacian V is alpha squared V, then it looks like this, and B has to satisfy Bessel's function like this or like that with minus signs here, where phi and z are as before in the two possible cases. And these then are the IN Bessel functions of alpha squared minus k squared over alpha squared plus k squared. And the INs are these Bessel functions of imaginary argument, and they're called modified Bessel functions. Here's another example. I guess I can ask the students, do you want me to say something about this biophysical problem, or shall I just zoom on?
Yeah, I'd like to see it.
All right. Okay. I'm not going to go into it in full detail, but I'll give you the important parts. So suppose rho is the density of free charges, charges that are free to move in and out of a dielectric medium, as opposed to charges that are part of the medium that are bound to it by molecular forces. The time-independent Maxwell's equations then are Gauss's law, which is the divergence of the electric displacement D, and a static form. Oh, I'm also talking about electrostatics here. A static form, a curly equals 0, Faraday's law, and that implies the electric field is the gradient of a potential. Now, across an interface between two dielectrics with a normal vector n, the tangential field is continuous. So if you have one dielectric, another dielectric, two electric fields here, they have to be the same. On the other hand, the normal electric fields can vary because there can be a density of free charges stuck between the two dielectrics. Now, here I'll tell you some amusing things about eukaryotic cells. Basically, it's a phospholipid bilayer. Now, what's a phospholipid bilayer? Well, it's a lipid part. And what is lipid? Lipid's a fancy word for fat. And what is a fat? A fat is a chain of carbon atoms. If it's completely saturated, then each carbon atom is attached to a carbon atom ahead of it and to a carbon atom behind it. So that takes 2 of the 4 bonds of carbon. Then the other 2 bonds stick out and are grabbed by hydrogen atoms. So that's a saturated fat. And because it's saturated, the chain is basically straight. And because it's straight, these, if you have a lot of these molecules together, they can line up like logs. And what they create then is a sticky substance. And if it's inside a blood vessel, it can stop the blood from moving and cause a heart attack or high blood pressure or other bad things. So that's why saturated fats are bad for us. An unsaturated fat is one in which the carbon atoms sometimes have double bonds, and then you don't have 2 hydrogens, you just have 1. You might even have a triple bond, in which case you'd have only, you wouldn't have any hydrogens at all. Anyhow, these, if there are double or triple bonds, then the chain of carbon atoms is crooked. And if you have, and that's called an unsaturated fat because it's not saturated with hydrogen. You don't have as many hydrogen as the number of carbon atoms could accept. And so in the unsaturated fat, there's just no way of stacking them to get them to stick together. And so these are healthy fats like olive oil, saying. Anyhow, so a phospholipid is a fat molecule, chain of these carbon and hydrogen, and then a phosphorus atom and something attached to the phosphorus atom. And this phosphorus group up here is either a dipole or it's charged. And so it has electrical properties, whereas the fat Fats basically are kind of electrically neutral. I mean, it's true there are electrons and protons inside a fat, but basically viewed from a few nanometers out, it's you don't see anything electrical. Whereas with the phospholipid, the thing can be charged or it can have a permanent dipole moment. Anyway, the important thing here is that the area of the eukaryotic cell can be something like 300 million square nanometers. So kind of like a square nanometer for every American. On the other hand, the thickness of this phospholipid bilayer is only 5 nanometers. And so that's pretty amazing. It's a little bit like the Earth's atmosphere corresponding to the, and relative to the area of the Earth. Anyway, here's the thing that's really remarkable. I guess I'm didn't say it here. Well, this is a pity. I really should say that somewhere here, because the remarkable thing is that if you have a living eukaryotic cell, you have a potential difference between the outside and the inside of the phospholipid bilayer. By the way, when I said bilayer, what's going on is you have 2 phospho groups here, and then each one has a lipid, and the lipids meet in the center. And so roughly 4 nanometers of the bilayer is the fat, and the other nanometer is the 2 phospho groups at the ends of the 2 phospholipids, the inner one and the outer one. Now, the remarkable thing is that there's a potential of 50 millivolts, if I remember correctly. And let me write that down. I'm almost certain that's the right number. 50 millivolts. But now what's the electric field between the two? Well, if it's 50 millivolts divided by 5 nanometers, then that's 10. There's a 10 to the minus 9 in the denominator because it's nano. And so that's, and then there's a 10 to the minus 3 because it's millivolts. So that's basically 10 to the 5th volts per meter. That is a, did I have that right? Let me just make sure I've got that right. That's, no, it's 10 to the 7th. All right, if 10 to the 7th volts per meter. So that's 10 megavolts per meter. That is a higher electric field than in a than we can make in a laboratory. It's really a pity that I didn't mention what the potential difference was. When I wrote this section, I had been working on this and I just took it for granted and didn't bother to write it down. That's one of the errors, by the way, when people write, is they forget to say the things that are obvious to them, and as a result, leave people in the dark. Let me just to see if I can have, so Google this thing. So potential across cell membrane. Let's see if I can get an answer here. Yes, yeah, I was right. 40 to 70 millivolts. And so we are talking about 10 megavolts per meter. So that's an incredible electric field. And in fact, that's one of the amazing things about physics, is that as you go to smaller distances, the forces are very much greater than the ones we ordinarily see in real life on a human scale. It's because the distances are so short. And this potential, of course, is also why nerves can transmit signals, because what you do is you start you flip that potential at a certain point, and then that shoots a wave down the rest of the nerve. Nerve being a cell that, instead of being like that, is long, like spaghetti. Okay, here's another example, cylindrical waveguides. I think I should do this one, but I could do it tomorrow in the all right, I'm gonna do the waveguides tomorrow in the problem session. That may draw people into the problem session. Let me say now a couple of things about Bessel functions of the second kind. It's basically that the Bessel functions of the second kind, you can define them in terms of J nu and J minus nu. And what you do is you form this combination. Now, when nu is not an integer, this is a simple, well, it's not simple, but it's a ratio that's well defined for complex nu, or for non-integer nu. But as nu approaches an integer, which is what interests people basically, or what's probably more important, we've got a 0 in the numerator and a 0 in the denominator, and so we have to take the ratio of the derivatives. So we say this thing is, if we just set nu equal to n, we get 0 over 0, and that's not well defined. So what we're going to do here is we're going to say this is equal to 0 plus the derivative of the denominator and 0 plus the derivative of the numerator. And we take the ratio of the derivatives, and what we get is basically this expression. In the book, I had a slightly different expression, and I think maybe the one in the book was a slightly better expression. I changed at the last minute to something that, to this form, but I think I'm going to go back to the book, the original book version. Now, what are these y nu of z's? Well, these are ones that are singular as z goes to 0. And y0 is like a log. Y nu is a gamma function times z to the minus nu for positive, for real part of nu being positive. And for very large, well, they're oscillating like the other Bessel functions, 1 over root z times the sine. And I've got a graph of these look like this. Notice they're all diving toward, actually they're all diving toward minus infinity as rho goes to 0 through positive values. This is for integral values of nu. And because the integral values, again, are the ones where we've got to choose we have to take this, this is called the L'Hopital limit. When do we need these? Well, we need these if we're dealing with a problem in which either the physics is infinite at the origin, or we're dealing with a problem in which rho equals 0 is not part of the problem. In other words, it's not in the physical region. And in that case, you need to allow for the possibility of these functions occurring. Whereas if we know that the physics is finite and the whole region from rho equal to 0 to rho equal to infinity is part of the problem physically, then we don't need the y's at all. Okay, so Do we have any question? Because we're really out of time now.
We are out of time.
Yeah. I mean, but if you have a question, I'll go for it.